Itself is everything you'll see on the screen, and the audio is my voice. I'll try to repeat responses from you. I'll try to repeat those so that you can hear what the questions were or comments. But it's a great resource. Those are posted on the Blackboard in the class videos area. There's a link on the left side. Okay. Looking at the proportionality of the width and the height of a photo when you're magnifying it or shrinking it. So what is it that preserves the image? So that in order to preserve the image so that it's not stretched. You've all seen a TV, maybe your own or in the MU or something, where the image is stretched, right? Because they're taking because the screen isn't the way it's broadcast. Because the ratio of the dimensions of the screen is not how it's broadcast. But then the TV is taking the image and filling up the screen, right? And so that the image is distorted. And I hate that. I cannot watch TV or a movie. My wife doesn't even notice, but I hate it. I can't do it. Okay. So that's the idea of, in order for the image to be true, you've got to maintain that proportionality of width and height. Okay, so we've been talking about proportionality in terms of representation with tables. We've been looking at ordered pairs of numbers and analyzing using the different types of reasoning. Now we want to talk about graph, the graph of a proportional relationship of quantities. So how does this photo get represented on a graph? If we put the width quantity on the horizontal axis, we put the height quantity on the vertical axis, and we have a single photo, how does that photo get represented in the graph? Yeah. That photo, one photo. Yeah. Right, so we get a point, right? So there's going to be, you come out here on the x-axis for that width quantity, and then up for the height quantity. That gives us a single point, and that point represents a photo. It represents the two values, one of each, the quantity of width and the corresponding quantity of height. So a point represents two values of quantities in correspondence. So if we make so here we go. The width and height are represented by the resulting point on the graph. If we have a slightly larger photo, have a new width, W2, and a new height, H2, how does it get represented on the graph? Same point? A new point, right? A new point. Same idea, though. We're mapping out the width quantity and the height quantity, and that point represents now that ordered pair, a photo with a corresponding width and height. So a point on a graph is actually like a packet of information. It's two values that correspond. Same thing with smaller photos and larger photos. How many possible photos could we come up with and plot points for? Infinite number. So we'd be here the whole rest of the course, and beyond that, trying to draw every dot that represented all the possible photos, right? So we have a quick and easy way to represent every single point, which represents every photo. And what is that? Yeah, so we just connect the dots. We connect the dots. So how would the graph be different if those points, if I were able to remove those points, how would the graph be different? What it's representing. What it's representing. So if I leave the line there and take the points away, what changed? Nothing. Nothing. These are just now highlighting that the line is representing every single photo that we could come up with, and every single photo we could come up with is a point. Okay, so that needs to be your image. When you see a line or a curve on the xy plane, your image needs to be, what is it? A graph is? What does it consist of? No, so now I'm talking about the whole black line. What does that consist of? All possible points. A graph is a collection of points. That might be kind of new. So in the past you might have think, oh, it's just a stick or it's just a curvy wire that you move and flip and move around. Okay, but so now we want to make sure that we see it, whenever you have a graph, you see it as a collection of points. Each point is two values that correspond in terms of the two quantities we're talking about. So each point represents two values. Corresponding values of the two quantities. And the line or the curve then is every point representing every correspondence of the two changing quantities that we're talking about. Anybody have a question about that? Okay, and then you saw in the equation of that line is h equals 3/5 w. And this goes right along with our proportional reasoning. Which way of thinking about proportional quantities is the equation of the line? Is that scaling factor, constant multiple, or constant ratio? It's telling us that the height is always 3/5 of the width. Which one is that? Constant multiple. The constant multiple equation is the equation of the line. The height is always this constant multiple, or the height of a photo is always 3/5 of whatever the width is. Okay, so h equals 3/5 w. Is that h in terms of w or w in terms of h? This is really important language. We're going to see it all semester, so we got to have it down. H in terms of w, w in terms of h. H in terms of w. H in terms of equals some expression, something you crank on with w's that gives you h. That's h in terms of w. Okay, so now we're going to move on to something new. So did the video cover graphs that we just covered? Were there graphs in the video? Yeah, that same kind of thing. All right. Important to go over. So now we're looking at our 6x10 photo. All right, we know the relationship that cranks out the height for any given width. What is it? H equals? Okay, that's our relationship, our constant multiple relationship that cranks out a height given a width. So now what we want to talk about is we want to introduce two new quantities. The first is a change in width. So an increase or decrease, a change in width in inches. So rather than it being an actual width of a photo, it's we had a photo and we either made it wider or made it less wide. How much did we increase or decrease the width by? That's different than, that's a different quantity than the actual width of a photo. So the change in width in inches, and the symbol we use for change is Greek delta. So Greek delta means change, and so we just do delta W. And that is this change in width in inches. Similarly, delta H, change in height in inches. Okay, so what we're going to do is we're going to track some different photos here. And we're going to track the width and height of some different photos, which will be very easy because we know exactly how to crank out heights given a width. But then we want to look at comparing the change in width to the change in height. So let's start by, I'm going to make, I want to know how tall the photo, so we're starting with 6 by 10, sorry, 10 by 6. I'm going to start, and I want to know how tall the photo do I need to have so that its width is 11. How tall the photo do I need to have so that its width is 11? Should be able to get that really quickly if we're catching on here. So let's just use a fraction, so an exact value. How do we get the height given the width? Yeah, so it's going to be 3/5 times that width, 33/5. Using our constant multiple reasoning or the equation of the line that we came up with, we get 33/5. Okay, now I want a photo, and we're going to get to the changes in a second. We're just going to crank out some photos here. 13. I want it to be 13 inches wide. How tall? 39/5, right? Piece of cake. Okay, one more. Let's do 15. So now let's go right to 15 inches. How many? Let's keep it in fifths, so it'll be easier when we get to the changes. 45/5, right? Okay, so look at these first two pairs. So I want you to make an ordered pair in our change in width and change in height. Okay, a change in width and our change in height table here that reflects a change in width and change in height. So 6, well, we're going to write 6 as, how many fifths is that? 30/5, okay? So looking at those first two ordered pairs, what's the reflected change in width and corresponding change in height? Go, see if you can come up with that. So what's the change in width and change in height given those first two pairs? Okay, so 1 3/5 has been offered up. What do you think? Agree? Yeah. That's what it is. We changed the width by 1. Let's go back to that example here. So 11. So then that means this delta width right here is 1. And what was the resulting change in height? 3/5 in order to make this 33/5. Okay, so now what I want you to do is use ordered pairs on the table to find out you can get changes in height for all these changes in width using the photos that we came up with in the left table. So you do that. So how much does the height change when we change the width by 2 inches? How much does the, etc. So you finish the table now. So which two can you look at to see a change of width of 2? Yeah, so you can look at the change. So you don't have to start at 10. So when you say a change in width, that can be starting at any size photo. So we can start at 11 and go to 13. And that's going to be a change in width of 2. What's the corresponding change in height? 6/5. Where in here can we see a change of width of 3? 10 to 13. And what do we get for the change in height? 9/5. Where can we see 4? From what to what? 11 to 15. We can see 4. And how many fifths does it go up? 12/5. So let's examine this table. Can we make a hypothesis here? Can we make a conjecture about what's happening in the relationship between change in width and change in height? He said they're also proportional. Is that what it's looking like? More than that, other observation. Yeah, scaling factor will work. What do you notice?
Changes in multiple of the formula.
Think. Yes. Well, times what? So the constant multiple is 3. 1 times 3 is 3/5.
3/5 is the constant multiple.
Is that familiar? 3/5. Is that a familiar constant multiple? Why? What is it? It's the same one we had when we started with the original quantities, right? So we've got these original quantities in proportion with a constant multiple or a constant of proportionality of 3/5. And now we're examining a change in width, different changes in width and corresponding changes in height. And what it looks like, this isn't proof, this isn't formal proof, but what it looks like is those are also proportional with the same constant multiple. So here's how we can show, indeed, that that's true. How would we write a change in height? A change in height is really looking at 2 heights and doing what? Yeah, so it's looking at the final height and the initial height, right? And then subtracting, right? We take the final height minus the initial will give us a change in height. So that's the operation or the computation behind this delta. Would be final minus initial. All right, well, what is H2? Looking at this, what is H2? It's just 3/5 times W2. And what's H1? 3/5 times W1. Factor out 3/5. What is W2 minus W1? Delta, that's the change in width, right? So what do we get? No matter what change in height that we pick, see, this represents now every change in height. Every change in height. And mathematically we showed that every change in height is equal to 3/5 times the change in width. That proves our conjecture. That proves what we were guessing, that now we know for sure that delta H equals 3/5 delta W. And what does that say about delta H and delta W? That they're proportional with a constant of proportionality or a constant multiple of 3/5. That proves what we kind of guessed there by looking at the table. Do you follow it? Does it make sense?
Will it always be the same as the original equation?
You tell me. Who asked? Who asked that? Yeah, so will it always be the same? So if we had a different constant of proportionality here, so say it was 2.2 was our constant of proportionality, what would we get? Everything would be the same, and we get delta H equals 2.2 delta W. Does that answer it? Okay. Any other questions? All right, so I want you to go on, I think it's on page that looks like this. Is it 29 in your book? Workbook?
Yeah.
Page 29 in your workbook. What does the line represent? What is it? A collection of points. So when you look at that, you see, oh, it's just a zillion points. Each point represents 2 quantities. In this case, what does each point represent in our context? A photo, right? Each point is a photo, the width and corresponding height together. So now, we're going to come along here and it says, represent a 5-inch wide by 3-inch high photo. So that must be one of the points on the graph, right? Boom. How did I just change the graph right now? How did I just change it? What's that? I didn't. All I did was highlight one of the many points that that line represents. Graph is the same. I just highlighted one of the points. How can I illustrate an increase from there? So I've got a 5 by 3 photo, 3 by 5. I want to increase the width by 2.5 inches. How could I illustrate that or represent that on this? This is really important. On this, what would I do to show an increase of 2.5 in width? Yeah.
Go over 2.5 squares on the W-axis.
Which way?
To the right.
From there, I could go over 1, 2.5 squares. That segment right there represents delta W of, we're going to do this a lot. This is how we represent a change in one quantity. You're going to go along parallel to whatever axis that quantity is on, right? So we just went, increased width by 2.5. So we went to the right because our width axis is our right and left axis. So now, is this a valid photo right there? No, if we change the width by 2.5, what do we find? Delta W equals 3/5 delta H. Nope, other way around. Delta H equals 3/5 delta W. What's the corresponding change in height that we'll need to preserve the photo if the change in width is 2.5? 2.5 times 3/5, which is 1.5. So now we've increased the width 2.5 and we want a valid photo. How do I show the change in height that will get me a valid photo? Go up. And how far will I end up going up? And how far will that be? That will be the delta H, the 1.5. So that represents the delta H. This represents the delta W right there. And that gives us our new photo. I want you to do the same thing starting at a width of 14. Go. The photo that has a width of 14 represent increasing the width 2.5, and then the corresponding change in height. Sorry, that should be horizontal and straight right there. What's the height when the width is 14? $8.5. If I do delta W of 2.5, what's my new width? My new width is 16.5. 14 plus 2.5. How do I get the new photo? I need a delta H of. So the question is it the same delta H? What is it about the graph? What is it about the nature of the graph, the line, that makes the change in height always 1.5 if the change in width is 2.5? Okay, proportionality, but what keeps it the same change in height for a given change in width? Yes.
It's a linear graph.
Yeah, it's a line. If that thing curves, then we're going to start getting different changes in height for the same change in width. But if it stays straight, then every time we take a 2.5 change in width, we're going to get the same 1.5 change in height. So let me show you that. Ready? Here we go. Change in width, delta W. Change in height, delta H. How's that shown on the graph? That's what we did. A little line segment this way shows a change in W. Line segment up and down, change in height. So, will we always get a change of height of 1.5 for any change in W?
Yes.
See? Doesn't matter where you start. Doesn't matter at what photo you start at. If it's a line, if it's straight, every time you increase 2.5, you require a 1.5 increase in height. And that was this that we proved that if the quantities are proportional, then the changes are proportional with the same constant of proportionality, the same constant multiple. Okay, get started on your homework soon. And take the pretest. Take the pretest.